Hello, welcome to Econometrics Melody. In this video, we'll discuss about the interval estimation. In our earlier video, we have seen that if a random variable x, this is normally distributed with mean mu and variance sigma square, then x minus mu divided by sigma, this has a standard normal distribution with mean 0 and variance 1, and this is the graph of our standard normal distribution. Similarly, we have also seen that according to our central limit theorem, for large n, the sample mean is normally distributed with mean mu and variance sigma square divided by n, and similarly we can construct a z-score, and that is equal to x bar minus mu divided by the square root of the variance of the sample mean, and this again is the standard normal distribution with mean 0 and variance 1. Standard normal distribution is symmetric, so in order to construct the interval of the estimate, we need to know about these two terms where significance level or the level of significance is alpha, which is also called is the type 1 error. This represents the error by chance, so it is represented here at the extreme, and if we suppose alpha to be 5%, then for the symmetric graph like the standard normal distribution, we divide it into two equal parts. So for 5% significance level, we divide it into two equal parts, 0.25% in each of the left and right extreme. So this is what we mean by half of the alpha. If our alpha is 5%, it is 2.5% on each of the extreme, and for this alpha by 2, we can calculate the z-score represented by minus z alpha by 2 towards the left and plus z alpha by 2 towards the right, and confidence level is given by 1 minus alpha. As they are symmetric in case of standard normal distribution, the probability of z being less than minus z alpha by 2, so this should be equal to alpha by 2, and due to their symmetric nature, the probability of z being greater than alpha by 2 should also be equal to alpha by 2. Z alpha by 2 and minus z alpha by 2, they are the score. Is, for example, for two-tailed test, if our alpha is 5%, then alpha by 2, this is equal to 2.5%, and the confidence level, this is 95%. And what is our z-score? Z alpha by 2, this is equal to 1.96. So here it is minus 1.96, and here it will be plus 1.96, and the probability of z being greater than 1.96 is equal to 2.5%, and the probability of z being less than minus 1.96 is equal to 2.5%. And due to the symmetric nature of the standard normal distribution, we can write the probability of z less than minus x. This is equal to the probability of z being greater than x, this extreme part. So if our significance level is 5%, then our confidence level is 95%. Then if we perform our experiment 100 times, then 95% of the time, the true mean of the population, it lies within the confidence interval created out of the sample mean. Now let us calculate the interval estimate of the population mean, and we know that according to the central limit theorem, for large n, the sample mean is approximately normally distributed with mean mu and variance sigma square divided by n, and from this result we can write it as x bar minus mu divided by sigma root n. This is normal distribution with mean 0 and variance 1, that is our standard normal distribution. So this is also our z-score. So this follows a standard normal distribution. And if we perform an experiment, let us say we want to consider our error as alpha. So as standard normal distribution, this is symmetric. So on the extremes, we have divided it by 2. So alpha by 2 and alpha by 2. Confidence level, it is 1 minus alpha. For this area, alpha by 2, we can calculate the z-score at the extremes, and they are equal and opposite. So this should be minus z-score when the probability is alpha by 2. And here we have plus z-score when the probability is alpha by 2. So in terms of probability, we can indicate this information as this z-score, probability of it being greater than minus z alpha by 2 and less than plus z alpha by 2, this is equal to 1 minus alpha. So in other words, the probability of this z-score lying away from the type 1 error, that is lying in this region, this is equal to 1 minus alpha. So as these two scores, minus z alpha by 2 and plus z alpha by 2, as they are symmetric, we can write it as Now if we operate the cross multiplication, we get it as minus z alpha by 2 into sigma root n mu minus x bar is less than z alpha by 2, and we multiply by sigma by root n to this part as well. This is equal to our confidence level. Now let us take this minus x bar towards the left and right simultaneously, and this is equal to x bar minus z alpha by 2 sigma root n, and this is equal to x bar plus z alpha by 2 sigma root n, and this is again our confidence level. So the population mean lies in this interval. This is our lower interval and this is our upper interval, and the probability of the population mean lying within this interval is given by 1 minus alpha, and this is our confidence level. So the confidence interval of our population mean, this is given by, and the confidence level is 1 minus alpha. As for example, if we set our alpha to be 5%, then the confidence level should be 95%, and the z 2.5% each equal to the z score is equal to 1.96. So in that case, so the confidence interval. Similarly, for a 90% confidence interval, our alpha will be 10% in that case, and we substitute this 1.96 by 1.645, so we'll get our 90% confidence interval. And if we want our 99% confidence interval, then we substitute it by 2.575, and we get our 99% confidence interval. So from a sample, we calculate the sample mean, we know this value, and we are assuming that we know the population standard deviation and we know the sample size, and from the sample mean we subtract these values and we get our lower confidence interval, and we add the same value z alpha by 2 sigma divided by root, and we get our upper confidence interval. And our population mean, it lies within this interval, and our confidence level for that case is 1 minus alpha. So for significance level alpha, our confidence level is 1 minus alpha. The mean, the population mean lies within this interval, this percentage of the time. Now, in this case, we are estimating the interval of the population mean, and we are assuming that we know the population variance. So in that case, we use our Z score. But if we don't know the population variance, then in that case, we'll have to use a sample variance. In that case, our Z score, it turns into T score with n-1 degrees of freedom. So when the population variance is unknown, we estimate making use of a sample variance, and in that case, the confidence interval of the population mean, this is given by x bar minus, in place of Z we replace by the T distribution and alpha by 2. T distribution is also symmetric, and n-1 degrees of freedom, and we have, in place of sigma, we write it by years divided by root n. This is our lower interval and our upper interval, and again this is our confidence level. So one-sided lower confidence interval of the mean, and our significance level is alpha. Therefore, our confidence level is equal to 1 minus alpha. So as it is one-sided, we need not divide alpha by 2. So this is equal to, the lower bound is our minus infinity, and then we need to include the mean. So our upper bound is x bar plus, so this should be equal to z alpha and sigma divided by root n. And if we don't know the variance, we use t statistics. So this is equal to, and let us use our one-sided upper confidence interval. So in that case, confidence interval of population mean, this is equal to, so for upper case, we use the upper bound is plus infinity, and then our lower bound, we need to include mu in the middle. So we are left with this. This is equal to x bar minus z alpha and sigma divided by root n. We are assuming that we know the population variance, and if we don't know the population variance and we need to estimate it, we are going to use the sample variance. So in that that case p alpha n minus 1, and we need yes root n. So we use this when we know about the population variance, and we use this relationship when we need to estimate the population variance. That is when we don't know the population variance. So if we are considering about a one-sided confidence interval, then in that case for alpha 5%, so 0 5%, the score is 1.645 and our confidence level is 95%. And this z score 1.645, it corresponds to the alpha of 10% in two-tail test, that is for constructing two-side confidence interval, and in that case our confidence level is 90%. Similarly, for one-sided confidence interval, if our alpha is 2.5%, then our confidence level is 97.5%, and the z score for alpha 2.5%, this is equal to 1.96. And for two-tail test, if our alpha is 5%, then our z score is 1.96 and our confidence level is 95%. So the z score for alpha 5% in one tail is equal to the z score for alpha 10% for two tail. Similarly, the z score for alpha 1% in one tail is equal to the z score for alpha 2% for two tail. So this indicates that the z score for x% in one tail, this is equal to z score twice x% for the two tail, and depending on the alpha level as well as our one tail or two tail confidence interval, we can plug in these values, either the value of z score or the value of t score, and we can calculate the confidence interval of the population mean when we know the variance of the population or when we don't know the variance of the population. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.